Hi dear students, dear first course students of pharmacy faculty. I continue with you my online lectures on inorganic chemistry. I am Kamala Badalova, the assistant professor of general toxicological chemistry department. Okay, today our lecture, I will combine for you two lectures, fifth and sixth lectures. And our lecture, the topic of our lecture will be the 6th and 8th B subgroup elements. As you know, these elements related to D block elements. And in this slide, you can see the particle table of the elements, first B and 8th B subgroups. They are transition elements and they are also D block elements. D block elements, for example, first B, second B, third B, fourth B, fifth B, sixth B, seventh B, and 8th B subgroups. They are D block transition elements. Okay, now we'll start for the 6B subgroup elements. At first, from the chromium, you know that 6B subgroup elements contain the elements chromium, molybdenum, and the wolfram. Chromium has which electronic configuration? This is normally has this electronic configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. And during explanation of the chemical elements of the particle table, I told you that the elements of B subgroups, they have in last level two electrons in s orbital, but chromium and copper, they have just one electron in last s orbital. This is and in chemistry there this case, this phenomenon, this abnormal phenomenon, this like anomaly for the chromium and the copper. And during giving of the energy, for example, for us, for chromium, we can write this distribution of chemical elements in our orbitals. How can we extract chromium? Chromate with composition ferrum chromium 2O4 is the most commercially useful ore. Chromium ore is processed and purified into chromium 3 oxide. This is reacted very exothermically in a thermal style reaction with aluminium or silicon to free chromium metal. And you can see from slide our reaction with aluminium and with silicon, both reactions. About the chemical reactivity, chromium reacts more readily with acids than does either molybdenum or the tungsten or wolfram, though its reactivity depends on its purity and it can easily be rendered passive. But about reactivity of the chromium with halogens. Okay, chromium halogen 3. What is chromium halogen 3? It means that chromium here has oxidation degree +3. Appropriate from the chromium with halogen. Dehydration of the chromium hydrate. This is chromium chloride hydrate This is anhydrous chromium chloride and hydrated, but this is hydrated chromium chloride. Because this is what is SOCl2? SOCl2. This is we can use this compound as the agent for the chlorination at 650 degrees Celsius. Chromium will react with the chlorine. We can prepare chromium Cl3. This is solid. And reduction of the chromium chloride or the bromide with the hydrogen or the hydrogen halogenate gives the chromium halogen 2 in the oxidation degree of the chromium plus 4. Reactivity of chromium towards oxygen and non-metals. Oxygen and preparation chromium oxides. Chromium reacts with oxygen to form oxides, but if chromium will react with oxygen, with of course with water, we can prepare chromium oxides, chromium 3 oxides. And by decomposition of the ammonia bichromate, also we can get to chromium 3 oxide. With non-metals and metals, chromium can react with the sulfur by the preparation of the chromium sulfide. With nitrates, with nitrogen, we can prepare chromium nitrates, chromium 3 nitrate and chromium. Okay, let my students will check which oxidation degree has chromium in this compound. About the carbides of following compositions and intermetallites with iron and the manganese. And in another involving table, my dear students, you can see the oxidation degrees of our ions in their compounds, our metals of their compounds. For example, for chromium, for molybdenum, and for wolfram, which compounds at first in oxides. Chromium we can dissolve readily in diluted hydrochloric acid, but if very pure, will often resist diluted sulfuric acid. Again, nitric acid, whether dilute or the concentrated. Okay. But by the decomposition of the chromium bichromate of the bichromates, we can prepare chromium oxide. At first, let us see the decomposition of the ammonium bichromate. By the decomposition of this compound, we can prepare chromium oxide, chromium 3 oxide, nitrogen, and the water. By decomposition of the sodium bichromate, we can prepare sodium chromate, chromium 3 oxide, and the oxygen. By the decomposition of the chromium carbonate, we can prepare chromium oxide and the carbon dioxide. And thus, by the composition of the chromium nitrate, we can prepare chromium oxide, chromium 3 oxide, nitrogen dioxide, and the oxygen. And let us see, write a plausible equation to explain the reaction shown in figure, in which pure ammonium dichromate ignited with the match produces pure chromium 3 oxide. But this is a picture from the experiments of the decomposition of ammonium bichromate. This reaction called as volcanic reaction, like volcano, and this chromium 3 oxide, the formed chromium 3 oxide, we can use for the cleaning of our gold or the silver things. Chromium oxides can react. Chromium oxide 3 oxide can react with alumina, with sodium nitrate, with sodium bromine O3. We can react with then addition reaction for the sodium nitrate. We can add sodium carbonate, and for the sodium bromine O3 sodium hydroxide. And you can see the reactions, which compounds we can prepare from these reactions. Chromium 6 oxidation state, the chemistry of the chromium 6. When hydrogen peroxide is added to an alkaline chromium 3 solution, oxidation occurs to give the yellow chromate 6 ion. This is chromate in oxidation degree of the chromium 6 plus 6. And this reaction, we can describe this reaction by following ionic equation. Both hydrogen peroxide and chromium 6 compounds are oxidizing agents, but in alkaline solution, hydrogen peroxide is the stronger oxidizing agent. When the resulting solution from above is acid filled with dilute sulfuric acid, the orange dichromate ion, dichromate 6 ion, where chromium also has the oxidation degree plus 6, is formed. But in this reaction, chromium will not change its oxidation degree. Why? Because chromium in this compound also has plus 6 oxidation degree, and chromium bichromate anion has plus 6 oxidation degree, of course. The dichromate 6 ion is reduced in 2 stages by zinc dilute sulfuric acid mixture. Chromium 6 plus 6 will go to chromium plus 3. But by this reaction we can see from orange, well, we can prepare green solution of the chromium compound. And at last, from chromium, if we will prepare from chromium with plus 3 oxidation state, which has a green color, we can prepare also chromium plus 2 oxidation with oxidation state compound plus 2 blue color. The solution of this compound has a blue color. So chromium 2 is readily oxidized. Chromium bichromate with zinc and the acid aqua chromium, we can prepare chromium plus 3 with in plus 3 oxidation state, and also zinc cation and water. Chromium and also by this way, using zinc, we can get from the chromium 3 plus to chromium 2 plus, which has blue color. Potassium dichromate, it can be crystallized to high purity standard without water of crystallization, and is a valuable standard redox volumetric reagent. It can use to titrate iron to ions in solution estimate with dilute sulfuric acid using a redox indicator like barium diphenylamine sulfonate, blue color. The dichromate 6 ion is a strong oxidizing agent. Examples of oxidizing action: it oxidizes iodide ions to iodine. But in this reaction, from the iodide, we can get to free iodine. The released iodine can be titrated with standard sodium thiosulfate solution using starch indicator. Using starch indicator, you know that usually for iodine we can use indicator starch. What is starch? Starch, this is a polysaccharide, and with this as you see this is a titration method. From the black brown color we will go colorless end point with the indicator, of course, using indicator. Chromium now we continue also the chemistry of the chromium 6 dichromate, and the chromate equilibrium is pH dependent. This is our dichromate, chromate anion. This is chromate anion. As you remember, what is oxidation, dissociation process? You know, in dissociation process, we can remove one hydrogen. But if we have dibasic acid, our dissociation will go in 2 steps. This is first step where we can remove one hydrogen, and this is second step of the dissociation where we can remove remain hydrogen from our acid. But in each for each step, for each compound, we have the constant for the chromium 04 2 minus and the for hydrochromate anion. And for the dichromate, also we can write the following dissociation process. This is electrolytic dissociation process. Hence the variation found for the solutions of the chromium trioxide are pH more than 8. This is chromate, which has a yellow color. pH 2 and in interval from 2 till 6. This is hydrochromate and dichromate, which has orange red color. And at last dichromate is acid of this anion, which has pH less than 1. You know what is pH? pH, this is index of the acidity. Which test reaction we have for the chromium, where we can prepare what is test. In end of this reaction we will get sediment. For example, what is sediment which we can't dissolve in the water. Okay, in end of this reaction we can prepare chromium 3 hydroxide. This is sediment which has gray-green precipitate. Precipitate and sediment, they are same. And with sodium carbonate, if sodium carbonate will react with chromium chloride and water, we can prepare, of course, also chromium 3 hydroxide, same color, and sodium chromate will react with the silver nitrate by the preparation of the silver chromate and sodium nitrate. Silver chromate is precipitate which has a brown reddish color. And at last, sodium chromate can react with the lead acetate with the preparation of the sediment lead chromate and the sodium acetate. And lead chromate, this is sediment which has a yellow color. The test reaction for the chromium, and where we can use chromium, you can see the areas of the application. We can use chromium in more areas of our life. About the biological role of the chromium, as you are student of the medical university, you must know about the biological role, you must know about the application of these compounds in medicine and in pharmacy. Okay, chromium is an essential trace element in mammalian metabolism. In addition to insulin, what is insulin? Insulin, this is nature. Origin is protein. It is responsible for reducing blood glucose levels and is used to control certain cases of diabetes. Diabetes, I hope you know what is diabetes. Diabetes is a disease. It has also been found to reduce blood cholesterol level by diminishing the concentration of bad low density lipoproteins in the blood. But how can we use chromium in pharmacy? Chromium is an essential trace element. Chromium plays a role in the metabolism of glucose and it's necessary for energy production. Chromium picolinate or chromium nicotinate complex influences carbohydrate, fat and protein metabolism. It assists in the management of fluctuating blood sugar levels in healthy people. A high dietary intake of refined carbohydrates needs more chromium. Okay, in our slide you can see the source of the chromium, for example cheese, meat and another sources of the chromium. Now we will go to the 7th B subgroup element, and first element of this group, manganese. Manganese is obtained mainly from the mineral pyrrolizate. Pyrrolizate, the structure, the formula of the pyrrolizate is manganese dioxide. Ferromanganese alloys are wear resistant and shock resistant and are used for the railroad tracks, bulldozers and road scrapers. Manganese oxide is the starting point for making most other manganese compounds. Potassium permanganate is potassium permanganate is an important oxidizing agent that is used in both analytical and organic chemistry laboratories and in water treatment. You can use manganese, potassium permanganate, this compound of the manganese. Manganese, you know that this trace element, cofactor of enzymes, superoxide dismutase, pyruvate carboxylase. Potassium permanganate, or another name kali permanganase, but if you will see the reagent in bottle, you can see this name, kali permanganese. In water dissolves to give deep purple solution. Strong oxidizing agent, dilute solution can act as the disinfectant. But the manganese 7, manganese with oxidation state plus 7. Manganese is in its highest oxidation degree, therefore manganese 7 will be an oxidizing agent occurs in the purple tetraoxomanganate or manganate ion. What is tetraoxomanganate? Tetraoxomanganate, it means here we have 4 oxygen atoms. It acts as an oxidizing agent in acidic or alkaline solution. In acidic, for example, you can see this equation of the reaction. We can prepare manganese 2 plus solution. But in alkaline, we will prepare manganese dioxide. And if we will make some experiment with manganese compounds in different oxidation degrees with an ion where manganese has oxidation state plus 7. This is original from the original dark purple manganate, we can get to the green manganate, where manganese has oxidation state plus 6, and we can further reduced by the further reduction of this compound of the manganate, we can prepare black precipitate manganese dioxide, where manganese has the oxidation state plus 2. This is manganese plus 2 cation, and another 2 compounds, they are anions. About the biological role of the manganese. Manganese is regarded for the metabolism of proteins and fats. A partial list of manganese-dependent enzyme families includes oxyreductases, transferases, hydrolysases, lyases, isomerases, and ligases. Manganese is involved in the function of numerous organ systems and is needed for normal immune function, regulation of blood sugar, production of cellular energy, reproduction, digestion, and bone growth. Manganese works with vitamin K to support clotting of the blood. The National Research Council has recommended an estimated safe and adequate daily dietary intake for manganese of 2 to 5 mg per day for adults. In pharmacy, manganese has been examined as a treatment for a variety of conditions, including osteoarthritis and wound healing. However, manganese is often used in combination with other vitamins and or minerals. Therefore, the effect of manganese alone are difficult to determine. Manganese in combination with calcium and zinc may be beneficial in patients with chronic wounds. A combination of calcium and manganese may alleviate symptoms associated. Source of manganese. Excellent food source of manganese include mustard greens, kale, chard, raspberries, and another foods or the vegetables, they contain manganese. For example, cinnamon, thyme, black pepper, and the turmeric. Which fruits, grapes, for example, contain manganese. Manganese measurement, how we can measure manganese. Colorimetric method depends upon oxidation of manganese to 7. Manganese 7. Forms highly colored permanganate ion obeys below visual or photometric comparison. As metal, we can analyze metal containing compound by ICP method and atom adsorption spectroscopy methods. We can determine our metals. You know that manganese also metal. What is persulfate method for the measure of manganese? Ammonium persulfate is oxidizing agent, but here we can use chloride interference. Because of reducing action in acid medium, use mercury 2 plus for the interference. Mercury 2 chloride complex is formed. Silver 2 plus is used as catalyst, and oxidation of manganese in low valence to permanganate by persulfate. In this reaction, you can see permanganate colored. Now we will start to the elements of VI-VIII B subgroup, the iron triad: iron, cobalt, and nickel. Iron is the fourth most abundant element in Earth's crust. Cobalt and nickel aren't nearly as common. All three elements form 2 plus and 3 plus ions. The most common ions of cobalt and nickel are the 2 plus. But for the iron, the most common ion of the ferrum of iron is the 3 plus, due to the half-filled D subshell. Ferrum 2 plus, ferrum 3 plus. In ferrum 3 plus, we can see that all electrons in D orbital, they are single. But in ferrum 2 plus, in 3D orbital, just 4 electrons, they are single, but another electrons in D orbitals, 2 electrons in the pair electrons. Ferromagnetism. What is ferromagnetism? The iron triad exhibits ferromagnetism, which is a much stronger magnetic effect than a paramagnetism. A ferromagnetic solid consists of regions called domains, in which atoms have their magnetic moments aligned. When this magnetic field absent here, but here in presence of the magnetic field. The paramagnetism and Dawn pictures describe the ferromagnetism. When placed in a magnetic field, all the domains are aligned and the solid becomes magnetized. Let we will see now some examples of variable oxidation state in the transition metals for iron and for manganese. Iron has two common oxidation states, as I told, +2 and +3. For example, ferrum 2 plus and ferrum 3 plus. It also has a less common plus 6 oxidation state in the ferrate ion ferrum 042 minus. But how can we write the acid of this compound? H2 ferrum 042 minus. Manganese. Manganese has a very wide range of oxidation states in its compound: plus 2, plus 3, plus 4, plus 6, and plus 7. Okay, when we say about the iron triad, so think about the typical transition metal, both transition metals iron. Here are the changes in the electronic structure of iron to make the 2 plus or the 3 plus ion. Ferrum atom has the electronic configuration 3d6-4s2. Ferrum 2 plus has the oxidation state 3d6. But what is 2 plus? 2 plus, it means that ferrum here lost 2 electrons, because the oxidation state of the electronic configuration of this oxidation state will be 3d6 and 4s0, because we will remove these electrons from s orbital. And electronic configuration of ferrum 3 plus, it will be 3d5. We will remove the electrons from two electrons from s orbital and 1 electron from d orbital. The 4s orbital and the 3d orbitals have very similar energies. There isn't a huge jump in the amount of energy you need to remove the third electron compared with the first and second. The figures for the first 3 ionization energies for iron compared with those of calcium. Okay, you can see first ionization energy, second ionization energy, and third ionization energy. There is an increase in ionization energy as you take more electrons of an atom, because you have the same number of protons attaching fewer electrons. Iron about the is important microelement. Human body contains 4-5 grams of the iron. Functional form: hem, iron proteins, hemoglobin 70%, myoglobin 5%. Some enzymes, non-hem iron proteins. And transport form: transferrin. Storage of iron: ferritin, hemosiderin 20%. Iron in food 10 in interval from 10 to 30 milligram per day, and absorption just only 7 from 7 to till 10% of the ferrum will absorb. Okay, but if for 1 milligram per day, this is 1 milligram per day. But when iron reacts with acids, it gives rise to iron 2 ferrous salts. Aqueous solution of such salts contains the pale green octahedral hexaaquarine 2 iron. This is dirty. From the pale green we will get to dirty green precipitate. If it only redissolves in very concentrated hydroxyl alkalis, but on standing in air it slowly turns a rusty brown color due to oxidation of iron 3. Increasing the pH renders iron 2 unstable. Okay, dirty green, dirty brown color. But of white color iron 2 carbonate, ferrum carbonate precipitated. Iron with ammonia, iron 2 hydroxide precipitated, insoluble in excess ammonia. Volumetric iron 2 in oxidation degree 2 can be analyzed by titration with a potassium manganate in acidic solution, sulfuric acid, for example, we can take for this method. No indicator is required. In this titration method, we will not use indicator. And aqua solutions, ferrum 3. Aqua solutions contain the yellow-green octahedral hexaquaran ion, 3 ion. It behaves as a typical metal 3 ion. From yellow we go to the brown precipitate insoluble in sulfites. In carbonates, we will prepare rusty brown precipitate again. The carbonate is not precipitated, but the hydroxide is. High charge density of the metal 3 ions makes the solutions too acidic to form the carbonate. Carbon dioxide evolved. Ammonia. With ammonia, our ferrum can react with the preparation of the rusty brown precipitate, and at last with the rhodanite. With the rhodanite, we can prepare blood red color. This is blood red color, very sensitive. A blood red color confirms ferrum 3 ion. No reaction with the ferrum 2. This one picture from our compound where iron with the copper sulfide solution will go to the iron 2 sulfate solution. This is just iron, free iron will react with the copper sulfate solution, and we can get to the just copper coating and the iron 2 sulfate solution. Hem iron proteins, hemoglobin can play the role, the function of the hemoglobin can transport oxygen in blood. In red blood cells, tetramer 4 subunits, each subunit 1 hem and 1 globin. Myoglobin, oxygen storage in muscle cell. Cytochromes, electron transport, their function is based on ferrum 2 plus reduced to ferrum 3 plus. Non-hem iron proteins, this iron sulfur proteins, transferrin blood plasma protein, beta 1 globulin, transport of the iron. One molecule of transferrin can carry 2 iron ions in form of ferrum 3 plus. Ferritin, intracellular iron, storage protein, liver, bone marrow. One ferritin complex can store about 4,500 ferrum 3 plus. Ferritin without iron, apoferritin. Then last, hemosiderin, damaged ferrum, iron overloaded ferritin. Iron from it is less available. Let's go to the overview of iron metabolism. Okay, food. From the food, our iron will go to the blood plasma, transferrin. From the transferrin, bone marrow ferritin. From ferritin, red blood cell hemoglobin. From the red blood cell to the bleeding iron places, and which spleen ferritin. From spleen ferritin blood plasma, and from blood plasma we go to the liver ferritin, and from liver ferritin hemocysteine, and from blood plasma we can get to the muscle myoglobin and tissues cytochromes. Proteins. Iron metabolism, unique reutilization, closed system, no regulated exertion system for the iron. Iron absorption must be regulated. Loss of iron, loss of blood. Families. Iron deficiency, microcystic anemia. You know that what is hemoglobin? Hemoglobin is a part of the blood. You know that hemoglobin consists of two parts, hem and globin. Globin, this is a protein, but in hem we have this complex compound which has the central atom iron. But if we have some deficiency of iron, we can get this is anemia. Iron overload, hemochromatosis, accumulation of iron in the body. This deposition as the hemocysteine. This iron absorption, food which contain ferrum 3+ will is reduction process. In reduction process we can get ferrum 2+. Ferrum 2+ in organism also will get to the ferrum 3+. From the apoferritin will get to the ferritin. This is like reversible process in intestinal mucous cell. Then from the ferritin, also ferrum 2+ will go to the blood transferrin, and in blood transferrin our ferrum 2+ will transfer to ferrum 3+. At last, in the stomach, you know that in stomach we have the acidic medium, which has a pH 1-2. Then we have ascorbic acid and the gastroferrin, iron binding protein. For example, ferritin, the metalloprotein that stores iron in the body. We told that in mammals iron is found and transported by the serum protein transferrin, and it is stored by ferritin in most life forms. Ferritin is a spherical molecule with an outer coat of protein and an inner core of hydrous ferric oxide. This ferric oxide. What is hydrous? Which contains some molecules of the water. As many as 4,500 atoms of the iron can be stored in a single ferritin molecule. This ferritin molecule where we have like 4,500 atoms of the iron. A three-dimensional representation showing ferritin, the iron storage protein in the body. Ferritin has a spherical shape, and iron brown is this iron, which has a brown color, is stored as a mineral inside the sphere. We don't yet fully understand the control of the iron blooding during the abundance and mobilization during scarcity. About measure, how we can measure iron. Interferences, phosphate, heavy metals. You know that iron, heavy metals. Interferences, phosphate, heavy metals. 1,10 phenolphthalein combines with iron 2+ to form complex iron orange in red color. Color produced confirms Bohr law, like in the case of manganese, visual photometric comparison. And all metals, all transition metals, they have ability to form complex compound. Complex compound, we can name a complex compound as coordination compound 2. As you remember, my dear students, coordination compound was the last topic of the first semester of the general chemistry. Okay, today I will finish with you these two combined lectures. Okay, thanks for the watching and the listening. I hope you enjoyed this. Okay, my dear students, stay at home and protect your health. Ciao and see you soon.